In this video, we're going to look at improper integrals. So what are they and how do we solve them? Let's take a look at what is an improper integral. Sometimes you might encounter problems which the boundary include infinity, such as this. In these examples, either your upper boundary or lower boundary or both of the boundaries are infinity. That's what we call an improper integral. So from its name, you might have guessed, it's not appropriate to take the integral just like this. Therefore, to better handle this, we want to express the integral in terms of limit. Let's use this as an example. We want to rewrite the integral in terms of limit for the boundary. In here, we are introducing an arbitrary variable b, which the limit of b goes to infinity, and we use the variable b to replace the upper boundary of our integral. The solution for the improper integral could have two results. One is converges, means the limit exists and is finite, means your integral converges to a value. The other one is diverges. Diverges means the limit does not exist or is infinite. To show it in a graph, we know the integral is kind of like a limit under a curve. So if we have a curve like this, if you're taking the integral, which is the area below the curve, from a to infinity, converges means the area below this curve is a definite value, which in our case, you see that as you goes to infinity, the area of this part converges to a certain value. Whereas if the function diverges, let me show you a different graph. In this case, we can see as we go to infinity, the area under the curve really grows to be larger and larger. There's not a finite value for that. That's what divergence means. Okay, let's look at some examples. For example, we have integral 1 to infinity 1 over x squared dx, which we write in terms of limit. That's going to give us the limit as b goes to infinity, the integral from 1 to b, 1 over x squared dx, which we don't change the function here, And let's take the antiderivative of this part. We would get the limit as b goes to infinity. So here we have x to the negative second power, which the antiderivative is going to be negative x to the negative 1, which gives us negative 1 over x. That's the antiderivative of this function. And evaluate from 1 to b. Just like how you would plug in for a normal integral, we would get negative 1 over b minus negative 1 over 1. So let's simplify this. Minus minus becomes plus 1. And as b goes to infinity, 1 over infinity becomes a very small number close to 0. So we know that part is equal to 0. So the limit becomes 1. And 1 is a finite number. So that's why we know the integral converges to 1. So that is an example that the improper integral converge. And let's look at a diverge example. First step, let's rewrite it in terms of limit. We would have the limit as b goes to infinity, the integral of 1 to b, 1 over x dx. Then take the antiderivative of your function. We would get the same limit. Antiderivative of 1 over x is ln of x, absolute value. Also evaluate from 1 to b. So what we would get is plug in ln of b minus ln of 1. And we want to evaluate that value as b goes to infinity, which we know ln of 1 is just 0, so we can remove this part. So the limit as b goes to 0, ln of b is also goes to infinity. So as our b goes to infinity, our value of the whole limit ln of b also goes to infinity. So after you evaluate the integral and plug in your values, the limit goes to infinity. That means this integral diverge.